5G has now come out of the labs and is preparing to become a daily tool of our life. It represents a communication highway that will allow you to travel on the internet with speeds unimaginable for previous systems. 5G may seem like technology from another planet, but it's just the brilliant result of the hard work of engineers and technicians. In this video, I will try to tell you in a simple way how 5G works and how we have developed a technique to measure its field level. What you are seeing is a signal received from a 5G mobile phone. The signal is organized in an ordered structure called a frame. Each frame lasts 10 milliseconds, so there are 100 frames in 1 second. On the vertical axis there are the indices of the so-called OFDM subcarriers, each associated with a frequency. The colors represent the received power in decibel milliwatts, a scale used to represent quantities with very variable amplitude. If we take a closer look at the structure of a frame, we see that it is made up of building blocks called resource elements, each of which carries from 1 to 8 bits. The areas in which the colors of the resource elements vary randomly are associated with the data transmitted to the users. However, there are more regular areas that are associated with controlled data, necessary for the operation of the system. There are many types of signals with different functions and structures. This, for example, serves to synchronize communication, and is called TRS. Coming back to the frame, we note that Rs have different colors, associated with different received powers. Most resource elements are used to transmit user data. Some, however, are used for transmission of control signals, which are distributed regularly in the frame. Among the signals, there is a particularly important structure, called the SS block or SSPBCH, which contains the basic information for accessing the network. It is formed by a block of signals, in the specific case 6, which are received with different power. This particular structure is linked to the characteristics of the antennas used in 5G systems. 5G systems use much more sophisticated antennas than those used in previous systems. For example, the SS blocks are transmitted through special antenna beams, called broadcast beams, which are used to transmit information of interest to all mobile phones. Let's look at the structure of the SSBs. Each SS block is associated with a broadcast beam pointing in a different direction. For example, the first SSB is associated with this beam, and is therefore well received by mobile phones that are along this direction. The second SS block is then broadcast in this new direction. Cell phones that are along this new direction will receive this SS block well. And so on. The base radio station thus covers the entire area of its competence, identifying the directions of the various mobile phones. The SS blocks are the only signals ever present, even in the absence of active cell phones, and are transmitted at constant power. They are therefore ideal candidates to be used as a reference for estimating the electromagnetic field level of the 5G signal. However, if we observe the figure of a frame, we notice that the SSBs are dominated by the data signals, and almost disappear as they are receiver at a lower power. This is a problem, as if we use SSBs, we will have an underestimation of the signal field level. To make things more complicated, our goal is to evaluate the signal field level under conditions of maximum power, that is, not in the measurement conditions, which are these, but in the worst possible conditions, which are these. To solve this problem, we need to go into detail on how the data is transmitted. The data is transmitted over another type of antenna beam, called a traffic beam. The traffic beam is much narrower than the broadcast beam, and allows the power to be concentrated towards the user, who has actually requested traffic, avoiding illuminating users who have not requested traffic. Let's follow the filling of the frame over time. Let's consider what happens at this moment, when the received power is relatively low. In this case, the user placed below in the figure has requested traffic. The beam carrying the data will be directed towards this user. The top measurement point in the figure will receive the signal along a side lobe of the antenna, and therefore the measured signal will be low. Subsequently, a higher signal is received, associated with the orange color. In this case, the user who requested traffic is the central one. The side lobe of the antenna pointing in the direction of measurement is however higher than the previous case, and therefore the field at the measurement point will also be higher. Continuing in the analysis of the frame, we arrive at a higher received power level, indicated with the red color. In this case, the field level measurement position is close to a mobile phone that has requested traffic. The data beam is then pointed towards the measurement position, which receives the maximum field level. So, the electromagnetic field level of a 5G signal measured at a point depends on the location of the user requesting the traffic at the time the measurement was taken. The problem of estimating the maximum field level in 5G is therefore a non-trivial problem. Italy has always been at the forefront of electromagnetic protection, often offering innovative solutions to the international scientific community. In the wake of this tradition, researchers from the University of Cassino in southern Lazio, Lazio, Piemonte, within the ISMA Center, have formed a working group on 5G. The solution we adopted was to use as a reference a particular signaling contained in the SS blocks, considering in particular the highest of the SSBs. In detail, the reference chosen is the PBCH DMRS, that is the reference signal for the demodulation of the PBCH channel. The power of the resource elements of this signal can be measured with great precision using a vector spectrum analyzer. A specially programmed mobile terminal is then used to force the data beam in the direction of the measurement point. A slice of the frame is then considered, chosen in such a way as to show both the SS blocks and the data channels. This slice can be easily measured using classical spectrum analyzers, and allows the estimation of the relationship between the maximum SSB power and the data traffic. The maximum power value that a resource element can assume is then calculated, then filling the frame with having the maximum power. The research was carried out with the utmost transparency, by publishing the results in open access peer-reviewed journals freely accessible on the Internet. Starting from the theoretical analysis of the measurement process, passing through the fine-tuning of the method, through laboratory measurements up to the tests on real systems, which were carried out thanks to the collaboration of Vodafone, which made a 5G system available for testing the method. The results confirmed the validity of the technique. It is also interesting to note that this method is the only one currently available, accompanied by the calculation of the measurement uncertainty. Research is ongoing, and we are currently studying new, even more innovative solutions, with the aim of further reducing the uncertainty range of the measurement. At the same time, we are studying different measurement strategies that allow the use of low-cost instruments, sacrificing as little as possible the accuracy of the measurement. "5G is the gateway to the future. Our effort is to allow you to fully use the incredible power of this technology in total safety."